Hi everyone, I will try to help you understand the Dijkstra algorithm. Let's start with navigation, definition of navigation. What is the navigation? Navigation is a field of study that focuses on the process of monitoring and controlling the movements of aircraft from one place to another. This algorithm is found by edsger. The Dijkstra algorithm used in computer science and bearing the name of the person who brought the algorithm to the literature is used to find shortest path, in the other words, graph in a given way. The algorithm is based on graph theorem, and this algorithm settlements are expressed points and rows. Rows are line and points are village, provinces, districts, etc. Next page. The Dijkstra algorithm is given and the source vertex in the graph, find shortest path from source to all vertices in the given graph. We maintain two sets. One set contains vertices included in shortest path tree. Other set includes not yet included in shortest path tree. At every step of the algorithm, we find a vertex which is in the other sets and has a minimum distance from the source. For a given source node in the graph, the algorithm finds the shortest path between that node and every other. It can also be used for finding the shortest path from a single node to a single destination node by stopping the algorithm once the shortest path to the destination node is determined. For example, if the nodes of the graph represent cities and edge paths represent driving distance between pairs of cities connected by a direct route. Dijkstra's algorithm can be used to find the shortest route between one city and all other cities. A widely used application of shortest path algorithm is network routing protocols, most notably intermediate system to intermediate system and open shortest path first. It is also employed as a subroutine in other algorithms such as Johnson, like this. And Dijkstra algorithm uses a data structure and mine priority. What is the mine priority? In computer science, a priority queue is an abstract data type, similar to regular queue or stack data structure, in which each element additionally has a priority associated with it. In a priority queue, an element with high priority is served before an element with low priority. In some implementations, if two elements have the same priority, they are served according to the order in which they were enqueued. While in other implementations, ordering of elements with the same priority is undefined. This is enough. This formula, where V is the number of nodes and E is the number of edges. Let's start. Dijkstra's algorithm. Algorithm is let the node at which we are starting be called the initial node. As initial node. Let the distance of node y be the distance from the initial node to y. Dijkstra's algorithm will assign some initial distance values and will try to improve them step by step. Mark all nodes unlisted. Create a set of all the unlisted nodes, call it the unlisted set. Assign to every node a tentative distance value. Set it to 0 for our initial node and to infinity for all other nodes. Set the initial node as current. For the current node, consider all of its unvisited neighbors and calculate their tentative distance through the current node. Compare the newly calculated tentative distance to the current assigned value and assign the smaller one. For example, if the current node A is marked with a distance of 6 and the edge connecting it with a neighbor B has length 2, then distance to B through A will be 6 plus 2 equal to 8. If B was previously marked with a distance greater than 8, then change it to 8. Otherwise, the current value will be kept. When we are done considering all of the unvisited neighbors of the current node, mark the current node as visited and remove it from the unvisited set. A visited node will never be checked again. If the destination node has been marked visited, or if the smallest tentative distance among the nodes in the unlisted set is infinity, then stop. Algorithm has finished. Otherwise, select the unlisted node that is marked with the smallest tentative distance, set it as the new current node, and go back to step 3. When planning a route, it is actually not necessary to wait until the destination node is visited as above. The algorithm can stop once the destination node has the smallest tentative distance among all unlisted nodes. For ease of understanding this discussion, use the terms intersection, route, and map. However, in formal terminology, these terms are vertex, edge, and graph, respectively. Suppose you would like to find the shortest path between two intersections and on a city map. A starting point and a destination, Dijkstra algorithm initially marks the distance to every other intersection on the map with infinity. This is done not to imply that there is an infinite distance, but to note that those intersections have not been visited yet. Some variants of this method leave the intersection's distance unlabeled. Now select the current intersection at each iteration. For the first iteration, the current intersection will be the starting point and the distance to it will be 0. For subsequent iterations, the current intersection will be a closest unvisited intersection to the starting point. From the current intersection, update the distance to every unvisited intersection that is directly connected to it. This is done by determining the sum of the distance between unvisited intersection and the value of the current intersection, and then relabeling the unvisited intersection with this value if it is less than the unvisited intersection's current value. In effect, the intersection is relabeled if the path to it true. The current intersection is shorter than the previously known path. To facilitate shortest path identification in pencil, mark the road with an arrow pointing to the relabeled intersection if you label or relabel it, and erase all others pointing to it. After we have updated the distance to each neighboring intersection, mark the current intersection as visited and select an unlisted intersection with minimal distance as the current intersection. Intersections marked as visited are labeled with the shortest path from the starting point to it and won't be revisited or returned to. continue this process of updating the neighboring intersections with the shortest distance, marking the current intersection as visited, and moving on to a closest unvisited intersection until you have marked the destination as visited. Once you have marked the destination as visited, you have determined the shortest path to it from the starting point and can trace your way back following the arrows in reverse. In the algorithm's implementations, this is usually done by following the node's parent destination node up to the starting node. That's why we also keep track of each node parent. This algorithm makes no attempt of direct exploration towards the destination as one might expect. Rather, the sole consideration in determining the next current intersection is its distance from the starting point. This algorithm therefore expands outward from the starting point, interactively considering every node that is closer in terms of shortest path distance until it reaches the destination. When understood in this way, it is clear how the algorithm necessarily finds the shortest paths. However, it may also reveal one of the algorithm's weaknesses, its relative slowness in some topologies. Let's next page. Proof. This is proof of the Dijkstra algorithm. Just read, no need to overdo it, just read. This algorithm will be very useful for the mouse to reach the cheese. The shortest way is red line from B and from B to H. From B to H, shortest way. You can use this code better understand. You can stop this video. Next page. This is a sample example. The neighbors of A are B and C. There are two ways to B. One is A and the other is A and C. Because of 2 plus 1 less than 4, the shortest way to B is A and C. Because 2 plus 1 less than 4. This less than this way. The algorithm initially assigns an infinite value, assuming that there is no access to all nodes yet. In other words, we are not able to go to any node yet. Then all nodes that are neighbors of the starting node are circulated and update the transportation distance to these nodes. After this update process, it updates the neighbors of the updated nodes and continues until all needs are updated and there is no new updates on the shape. But this algorithm weakness direction. If there is an edge with a negative value, the algorithm will not work successfully. This is because the minus value always gives a better result than the current state, and the algorithm has never been stable. Neighbors of the two nodes will be updated by the adding the minus value to each other in the two nodes. It will find a shorter path and update each other to achieve shorter results. Unfortunately, this process is the beginning of a process that goes on forever and never ends with a better result. A better state will be found constantly than the current one, and smaller values will be updated. Therefore, the Dijkstra algorithm doesn't work successfully in graphs with negative values.